All right, so we last week ended on thinking about confidence intervals where we didn't know what the population variance was, and all we had was this sample variance. So we worked through a couple examples in class, and then I said we'll kind of start today off. I'll show you how we would do this in Excel. Okay, so it's pretty similar to what we did when we had a known population standard deviation, with the exception we said we had to use that student t distribution. Okay, so we're going to start out kind of a reminder what we're looking at. We're going to build our confidence interval around our sample mean. And then, one second, I'll get everything up here. Instead of using a z-value that gives us alpha over 2 on each side of the confidence interval, we're going to have to look up a value that comes from the student t distribution. Which student t distribution depends on the degrees of freedom, which was n-1, or our sample size -1. And then now our standard deviation or sample means, the notation is a little bit different, only because it just signifies that we're not using a known population variance to calculate it, but instead of sample variance. Okay, so the procedure is very similar, but we're using a different distribution. So I've got here in that confidence interval blank, we kind of working off this one in the past. We looked at before, this is when we did the proportion and sample mean for the enrollment data. I'm instead going to go to this unknown pop SD, or unknown population standard deviation tab, where I've got a bunch of drug death data. I don't even remember why I had this, but it's kind of an interesting example. So we've got different counties, and I've got kind of two data sets. One where I've got 2012, another one where I've got 2016 data. Okay. So the first thing I'm going to do is find the sample mean. And here I'm going to do it for 2012. So I just go over here. And I think we'll do drug deaths per 10,000 people. All right. I select that variable, hit enter. Hopefully this is kind of getting easier. I'll use that count function to determine my sample size. And then I'm going to now, before I was given a population variance because I couldn't see the population data. Now I'm not given a population variance, so the best I can do is find a sample variance from my sample, or this is a standard deviation. I need the variance, don't I? So var.s, all right? So I go over, I find the variance or the sample variance here. Okay. Now I've got everything I need except for how many standard deviations away do I need to go, or what should that t value be? So remember, z value is supposed to the number of standard deviations away we were from the mean. The t value has a similar kind of interpretation, or at least we can kind of think about it in that way. Okay. Any questions over anything so far? This should be kind of a little bit review how we do this part. So now I'm going to do the same thing, but for 2016 here real quick. So I'm going to find drug deaths per 10,000 in 2016. I can do my sample size using the count function. And I can find the variance using that var.s function. Remember, control shift, command shift on a Mac is how I'm kind of doing that relatively quickly. Okay. So I've got 2012, 2016. Now, if I just look at the mean, I see the mean in 2016 is a little bit greater, right? But I mean, if I'm thinking about, I'm observing a sample mean, it could be the fact that for 2016, I saw a sample mean that was a little bit higher than what the actual population mean was. And in 2012, I could have seen a sample mean that was a little bit lower than the true population mean in 2012. So even though based off my sample, it looks like 2012 is lower, like I want to make sure that that's the case, right? So I'm going to build some confidence intervals. And I think we looked at this with the proportion examples, where if those confidence intervals overlap, I can't say that one is larger than the other or smaller than the other. If they don't overlap, well, then that's telling me that even if they were at kind of their extreme ends, that before we were kind of looking at Clinton's proportion versus Trump's proportion, now we're going to be looking at 2012's kind of mean drug death versus 2016's mean drug death. So if they don't overlap, I can say that with whatever level of certainty, 2012 drug deaths were lower. If they do overlap, I can't really say anything at those levels of confidence. So how do we find these t-values? Okay. So when we're using a standard normal distribution, we use the norm.s, the I and v, right? We're working in inverse, right? We had the probability, we wanted the z-value. Here, I still know the area I want, right? Alpha divided by 2. So I want to work in reverse here as well. So instead of norm.s to I and v, we're just going to use t to I and v, right? We're working, doing the inverse process, but using the student t distribution. What's the probability we want? Alpha over 2, comma, what's my degrees of freedom? Sample size -1. Questions on this? Now, what's one problem we talked about with the other examples we did in Excel? When I hit enter here, I end up with a negative value. But we said that's really already built into our upper lower bound equation, right? We use the negative t-value to get the lower bound, positive t-value to get the upper bound. Okay. So what was one way we said we could solve this problem? Yeah, I could just use the absolute value here. It drops the negative sign, so ABS function. Now, unlike the standard normal, one problem is I used to just be able to copy these down. We got some bad things happening here. Why is that the case? Oh, because my sample size wasn't changing, right? So go up here, I'm going to freeze using F4 or Command T on a Mac, going to freeze that sample size cell reference. Now when I copy this down, I've got my 3 t-values for the 3 different confidence levels that I want to create confidence intervals for. Okay. Questions here? Shouldn't be anything crazy. Now, in the other examples, I showed you how we could kind of calculate these intermediate, right? The standard deviation of my sample means or standard deviation of my sample proportions. I could use the same approach here, but instead, because I've already done that with the other ones, I'm going to show you what happens if I just want to do it all in one cell, do no intermediate calculation. So I'm going to be putting that equation into Excel, basically having Excel be my calculator. I take my sample mean, not add, I'm doing a lower bound, so I subtract that t-value multiplied by the square root of my sample variance divided by my sample size. Right. Now, I want to be able to copy this down to get my lower bound for the next 2 confidence intervals. But the only thing that should change for different, like the sample mean shouldn't change, sample size, sample variance shouldn't change. The only thing that I want to change, right, is the number of standard deviations where I need to go, or I want that t-value to change when I copy this down. So everything else, I'm going to freeze those cell references. All right, F4 or Command T. Now when I copy this down, everything up here has stayed the same, but that cell reference keeps updating. So I'm using whatever t-value lines up with the new alpha that I want for that confidence interval. Any questions there? You want to see one of these cells again? All right with this? Okay, and then to get the upper bound, I just go in, I double clicked on that cell so I can see the formula. I'm going to copy, hit enter to get out of the cell, paste it in. When I use this method, none of the cell references update, so everything should be the same. But now to get my upper bound, I just add that margin of error instead of subtract it. All right. So add my margin of error. Now when I copy this down, it keeps updating that t-value. Notice when I want to say things with higher levels of confidence, right? Because the alpha of 0.1 corresponds to a confidence level of what? 90%. 0.05 would be 95. 0.01 is 99. When I say things with a higher level of confidence, that means the area in my tails is getting smaller. So I'm going to have to kind of go further out from that sample mean and have a wider interval. Sure enough, when I say things with a higher level of confidence, I have to increase the size of my interval. So my lower bound is getting lower, my upper bound is getting higher. I'm getting this wider interval. Okay. That isn't the case. I know I made a mistake somewhere, right? So that's a good way to kind of check yourself as you're building these. No questions on this? No? All right. So we would do the same thing down here. I have to rebuild this here. So I go find my t-value. Now, here I've got the same sample size. So hopefully when I do this, I get the exact same values in both these places, right? So if I did t dot inv, alpha divided by 2, and then here I've got my sample size minus 1. Now, another way we said instead of using the absolute value is, if I want the positive value, I could just look at the right side of the distribution, right? Which would mean if I want alpha over 2 in the right tail, what area would I have to tell Excel? Well, I have to tell it the left, so 1 minus alpha over 2. So hopefully if I do it this way, if what I told you last week was true, we get the exact same t-value here, right? And then I think I need to freeze my sample size cell reference, copy this down, get the exact same thing. Now, what if like my sample size in the other year had been a little bit larger? Notice I'll get different t-values because every single sample size is its own degrees of freedom, has its own distribution. But I didn't, they were the same sample size, so that was kind of nice. So my lower bound, take this mean minus the t-value multiplied by the square root of sample size divided, nope, not sample size, sample variance divided by my sample size. And then said I had to freeze everything except for that t-value. So I freeze these cell references. I'm going to go in, copy, hit enter to get out of the cell, paste it over here to get the upper bound. All I have to do is add that margin of error. Now I can highlight both of these and copy them down all at once. And I've got my kind of 3 confidence levels. I did that kind of quick. So are there any questions over anything want to see a cell again? It was really the same process. I'm just doing this for both years to kind of make a point, I guess. Now, this one, if I just base it off my sample, it looks like drug deaths have increased from 2012 to 2016. If I look at, even at the 90% level, right? If I look at the confidence intervals, what? 2012 goes from 2.16 to 2.73. So this was 2012 confidence interval. Then 2016 goes from 2.19 to 2.8. This was 2016. I mean, there is significant overlap here, right? So if I'm just looking at the sample mean, it might look like they went down, but right, it's just based off of a sample. The true population mean could be anywhere within this range of values. So it could be that in 2016, the true mean is down here, and that the true mean up here in 2012 could be something like this, or maybe it's over here, and in 2016 it's here. So I can't really say anything, right? Because it could be, that it was larger in 2016. I just happened to get, one of the samples that came from over here. All right, so I know that confidence interval, can't really say much in this example. Now, if they didn't overlap, maybe I could, but that's not the case. Any questions over that? Okay, so probably won't give you a Excel example for one or Excel assignment for one population. I might, on the next Excel assignment, include like one question, but it probably won't have every single type here, right? It might just have a proportion, or it might just have a sample variance one, because eventually where we're going is we're going to do some stuff with 2 populations. And so that I think is probably what I'm going to save that Excel assignment for. But the next topic we're going to introduce is kind of be related to confidence intervals, but a slightly different way of testing certain values for the true population parameter. So we looked at this week's slides. We're going to start talking about the next topic, which is hypothesis testing. So I'll try to introduce the idea just generically. I don't know how far we'll get today, but we'll spend the rest of the week kind of talking about it. So make sure that I have this thing. So what we're trying to do, yeah.
Are we still set up to have the test next Friday?
So I'll probably move it forward to that following week. I don't know exactly if we'll do it that following Monday or Wednesday. I'll kind of wait and see where we're at the end of this week about exactly how far we're because I think we'll probably need another day or two. But I will. Might not happen today. I'll try to do it tomorrow. I will get up like the next set of practice exams. So obviously the last few questions we probably won't have covered it, but at least it'll kind of give you an idea where you can start kind of working through some of the older stuff. Yeah. Yep. So what we're doing with hypothesis testing. So I'm sorry, I got my mind. So confidence intervals. We're trying to say the true parameter, the true mean and true population proportion is somewhere in this range of values. Okay? Hypothesis testing is a little different in that we're going to start to test for whether that population parameter could be equal to particular values. Okay? Now it's going to be a little bit different, and I'll kind of connect the two probably once we explain what hypothesis testing is. Once we can actually work through some problems, I'll probably then go back and relate to confidence intervals. But for now, we'll kind of treat it as though it's kind of its own thing. Right? But they are very, very closely related. So what we're going to do with hypothesis testing is say, look, I don't know the true population mean or the true population proportion is. Okay? So I'm going to develop some hypothesis about where that value is going to be. So maybe I say something like, I don't know the true mean income in the US, but I'm going to create this hypothesis where I assume that it's greater than or equal to 50,000. We're then going to have an alternative hypothesis would be just the opposite of that. So if I assume it's greater than or equal to 50,000, the alternative hypothesis would be that it's less than 50,000. Right? These are kind of like complements, right? My null and alternative hypothesis. So the null hypothesis is what we assume is going to be true. The alternative hypothesis will just be the exact opposite of that. If I assume that the average income in the US is greater than or equal to 50,000, I then take a sample and I see that the average, the sample mean from that sample is 40,000. Maybe that's sufficient enough evidence, it's far enough away from what I assumed, that I'll actually reject my null. Right? If I assume it's greater than or equal to 50,000, with my sample of 100 people, I only see a sample mean income of 40,000. Well, what I assumed is probably wrong. So I should reject that null hypothesis or reject what I assume to be true. Now, I potentially don't have enough evidence, right? So let's say I assume it's greater than or equal to 50,000, and my sample mean income I see is $49,999. Well, that technically doesn't support my null, but right, even if the true mean population mean income was like 50,000, it's very likely I see a sample mean that's just below that. So sometimes we have evidence that goes against the null, but not sufficient enough. Right? We know that, yeah, I could very easily see something below 50,000, even if the true mean was 50,000. And so just because I have some evidence that goes against my null, I shouldn't always reject it. So kind of where's this line? Like what evidence is strong enough? What if I saw 48,000? That's my sample mean. Should I reject 50,000 or above as being the true population mean? What about 45, right? How low or how far away do I need to be from that 50,000 that I assume the income is greater than or equal to in order to reject my null? So that's kind of what we are going to try to determine, right? Where's that cutoff? Yeah. So I had this example where I'm kind of thinking about, I want to test for whether or not the average mass market beer, I kind of think about your traditional like Miller, Budweiser, all this stuff, has a lower ABV than I chose Bell's Too Hard, right? It has 7%. So I take a sample of 36 different mass market beers, and I find their sample mean ABV was 4.5. Right? So it's quite a bit different, right, than what I assumed. So I was going to test for whether or not they had a lower ABV than 7%. So what I do when I'm hypothesis testing is I stack the deck against myself. So if I'm wanting to test for whether or not that ABV is less than 7%, I assume the opposite is true. I assume it's greater than or equal to 7%. So whatever I'm trying to test for, that kind of ends up being my alternative hypothesis, right? I stack the deck against myself with my assumption and assume the opposite is true. So if I want to test for whether or not it's less than 7%, I assume it's greater than or equal to 7%. So, where do I have this? I'll come back to this in just a second. There we go. All right. So, right, what I'll assume is that it's not lower, that it's greater than or equal to 7%, right? Which I could kind of write like this. Right? So my null hypothesis is that that true population mean is greater than or equal to 7%, because what I was wanting to find or test for is whether or not it's less than 7. I stacked the deck against myself. I took that sample. I found a sample mean that in fact goes against the null. I believe the sample mean I found was 4.5, but doesn't go against the null enough. Right? So talk a little bit more about null alternative hypothesis here. I skipped a bunch of stuff. I just kind of wanted to connect that. I knew I had a slide in there. I didn't realize it was that far ahead. So there we go. So in a more general context, right, what we're going to do with these two hypotheses is the null is going to be what I'm assuming to be true, which is going to be the opposite of really whatever I'm trying to test for, which is my alternative hypothesis. We'll kind of write these as H subscript 0 for the null, H subscript A for the alternative. Right? Sometimes you'll see this as H subscript 1. I just always use A because I think it's a lot easier to connect. Like that makes more sense, right? The alternative hypothesis. So I kind of already showed you what they'll look like once we write them out. Right? We're going to make some assumption about the population mean or the population proportion, and then have the complement of that be the alternative. So we use our sample to see whether or not it contradicts the null or not. If it contradicts the null, then we have some work to do to say, does it contradict it enough? Does it go against the null enough? Because we know that sample parameters, they don't follow distribution. So even if I assume that that true population mean, I said it was 7 or higher. So let's just use the lowest value in that range of 7. Well, I know that my sample means will be normally distributed around this. And if the standard deviation is high enough, like I don't know, maybe it's like 5%, if the standard deviation is high enough in my sample means, well, then from any one sample, it might be fairly likely I see 4.5. Right? So I need to determine like how likely or unlikely was it if this was in fact the true mean, how likely or unlikely was I saw that value I did from my sample. How we can use some of the knowledge we have about how sample means are distributed to do that. I'm doing a lot of foreshadowing, but this is kind of the general idea. So we've got 3 scenarios. Right? I already mentioned some of them, but either we see evidence that's very inconsistent with what we assume to be true. So right, maybe if I assume the mean is 7, if I see like 1.2, well, I can probably reject my null. And if I see 6.3, it goes against my null, but not very much, right? So maybe I have evidence that's inconsistent with the null, but not very much, right? So if it doesn't go against what I've assumed, if it's kind of close to what I assumed, I would fail to reject my null. For evidence that goes against the null a lot, then I reject the null. Sorry. If it doesn't go against what I assumed by very much, I would fail to reject it. And if I find evidence that is consistent with the null, well, then why would I reject the null, right? If I assume that the true mean is 7 or higher, and I see something like 8.3, well, that supports the null. Why would I reject the null? I found evidence that supports it, right? So I would say I failed to reject. Now, sometimes we kind of see this as read as like you accept the null. If I find evidence that supports the null, I would accept it. You don't really want to say that. I think even the book sometimes has some like on the connect homework questions that we do some hypothesis testing with that. They might even say that you accept the null. You're not really supposed to say that. because you're still basing it off a sample, right? You're just saying, based off of my sample, I can't reject that null. I'm failing to reject that. You shouldn't say that I accept it, right? But it's a little bit of semantics there. So this was kind of those three scenarios. I find evidence that supports the null, so I don't reject it. I find evidence that goes against the null, but not very much, so I fail to reject. Or I find evidence that really goes against that null, and so I'm going to reject that null as being true. When I assume to be true, probably isn't. If I assume that the true mean is 7 or higher, and I see a sample mean of 1.2, I was probably wrong with my assumption. So another good analogy for this null alternative hypothesis is court cases, right? So if I'm thinking about what am I trying to test for, that should be my alternative hypothesis. In a court case, what am I trying to test for? Why does the court case exist at all? Yeah, it is the person guilty, right? You don't bring you into a court case because they believe you're innocent. They're bringing you there because they believe that you're potentially guilty. That's what they want to test for. So hopefully, what do? You should be innocent until proven guilty, right? So they want to test for whether or not you're guilty, so they assume the opposite is true, which is that you're in fact innocent. So the null hypothesis, we're stacking the deck against ourselves, just like in a court case. They want to see if you're guilty, they stack the deck against themselves and assume starting out you're innocent, right? Or at least they should. So then what's the alternative hypothesis? Well, if they're assuming that you're guilty, they're assuming that you're innocent, then the alternative would be instead that you're guilty. Right? So what we're doing with hypothesis testing is we're trying to see, can we find enough evidence that goes against the null, right? Goes against the person being innocent, so that we can reject it, right? If I can find enough evidence that the person is in fact guilty, right? Which would be finding evidence that goes against the null, then I reject the null, right? And you go to jail, right? So if I can find enough evidence that goes against that null that you're innocent, I convict you and you go to jail. If I can't find a lot of evidence that you committed the crime, like, yeah, maybe you didn't have an alibi, but we don't have any DNA evidence, we don't have any, anything, then right, you're free to go, right? We fail to reject that null. We don't have enough evidence that goes against the null. We fail to reject it, and you can go on about your way. We still assume you're innocent. And then, I don't know, some pun using some O.J. Simpson stuff. So this is kind of, I think, a good way to at least think about what we're doing and something that we've all kind of heard about, right? Court case. So we've got this null alternative hypothesis we talked about. There's really three different types of tests we're going to do for these parameters of the population proportion and population mean. So we'll start out today using the population mean. Okay? So we can assume that true population mean, right, is less than or equal to some value we choose. So this is like mu subscript 0. This is going to be some value that we choose, right? We assume that the true mean is less than or equal to this value. So then the alternative hypothesis would be that it's greater than that value. So it might seem kind of weird that this is the greater than test. So the name of the test is kind of based off of the sign in the alternative hypothesis. So the test that you're trying to find is, I want to find whether or not the true mean is greater than a certain value. So it's a greater than test. So we assume the opposite is true in the null hypothesis, that it's less than or equal to that value. So the name of the test is based off the alternative hypothesis. We can also say, okay, I want to test for whether or not the true mean is less than a certain value. So we stack the deck against ourselves with the null hypothesis and assume it's greater than or equal to that value. So notice here, the name of the test, greater than and less than, is based off the sign in the alternative hypothesis. So these are what we would call kind of one-sided tests, right? Notice if I assume that the true mean is less than or equal to a specific value, well then the only one side of the distribution will I find evidence that goes against that, right? Let's say I assume the true mean is less than or equal to 7, we get over there, right? Well, then if I see anything that's less than 7, that supports the null. The only way I could ever reject the null is if I see something on one side of that distribution, right? Something that is above that value of 7. Instead, we sometimes have a two-sided test, which is we want to test for whether or not the true mean is different than some value. Right? Maybe I want to test for whether or not the true average income is different than 50,000, not equal to 50,000. So I stack the deck against myself and assume it's exactly equal to that value. So we would call that kind of a two-sided test, or a two. I don't know why my arrows are so off there, but now we've got 2 one-sided tests and then 1 two-sided test, right? Because there, if I assume that the average income is equal to 50,000, well, then if I see a sample mean of 45 or a sample mean of 55,000, those both would go against my null. Right? Whereas one-sided test, only one of those would, right? Because I'm only considering one direction. Any questions? Clarification or all right. So we're going to identify what parameter we're interested in, either the mean or the proportion. That one's, I don't even know why I write this step in there. Right? Hopefully it's pretty easy to do this one, right? We identify if we're looking at a mean or proportion. You then determine whether or not you have a 1 or 2 tail test, right? And then one thing we have to be, I don't know, we'll start kind of noticing is we'll always include that equality in the null hypothesis. So when I'm identifying my null and alternative hypothesis, I need to make sure the equality is only included in one of them. Now, if you look at the previous slide, notice I always include it in the null hypothesis. Okay? Just kind of out of convention, that's how we do it. And I'm kind of reminded of that in the two-tailed test because the equality, the two-tailed test has to be in that null. And I'm assuming it's exactly equal to a specific value. Okay? Ultimately, in the end, once we start working through these, I'll show you it actually doesn't matter which, if we put the equality in the alternative or the null. But just out of convention, we'll kind of always try to include it in that null. Okay. So, start to actually see how we could solve one of these now. We go back to that example where I want to test for whether or not the average beard has an ABV lower than 7%. Right, what I want to test for is whether or not that true population mean that I can't observe. So what I want to test for is my alternative hypothesis. I want to say, is that true mean less than 7%? So I assume the opposite is true. My null hypothesis is that that mean is greater than or equal to 7%. So in English, I say the word problem it's giving us, we can turn that into, like I did up here on the board, kind of the statistical way we would write that. Okay. So I've got what? 1 or 2-sided test here. One side. Because what sample mean values would go against the null? Only sample mean values that are not greater than or equal to 7, but less than 7. Right? So only one side matters. Or one side would give the evidence that I could potentially reject the null. So what if instead I had an example like this? So what if an economist wants to test whether or not the mean retirement age is different than 67? So in English, I'm saying what I want to test for is this mean retirement age different than 67? So what would my alternative hypothesis be then? Yeah. Is the true mean not equal to 67? Yeah, different than really just means not equal to. So anytime I see this word like term different than, I should probably be thinking about a 2-sided test, right? Because if this is my alternative hypothesis, I put 0 in here. Sorry. 67, right? What would my null hypothesis be here? Yeah, just the exact opposite, right? So I want to test for whether it's not equal to 67. The complement of that is that it's exactly equal to 67. So that one's kind of a little bit easier. 10 minutes. I think I'm going to skip type 1, type 2 error stuff for today. We'll come back to that next class. So I want to actually show you how we would walk through this test. Okay? So we want to know if we find evidence that goes against, I wrote 0. Sorry, I don't know why I keep writing it. If we find evidence that goes against our null, how do we determine does it go against it or not? So we've got two approaches, the p-value and critical value approach. We'll kind of talk today about the p-value approach. Okay? So we've got this example, we've got our null alternative hypothesis. As I said, sometimes we'll write that as H subscript 1. I typically going to try to keep the mention of H subscript A, but you might see this, you see others with other sources. So we take our sample, we found that 4.5 from the 36 max market beers. But if we were to actually take that sample, we know that if what I assumed to be true was in fact true, and I use the lowest value in that range, so 7% is my assumed true population mean. If that was in fact the true population mean, my sample means should be distributed normally around that value. Right? The sample mean should be normally distributed around the true population mean, but I have a value that I've assumed that true population mean is equal to. I also know the standard deviation of those sample means should be equal to whatever the population variance is divided by my sample size, or if I took 36 mass market beers, be over 36. So kind of similar to confidence intervals, we're first going to start out with examples where we're given some known population variance. It's not very likely we have a known population variance if we don't know the population mean. But we need to start here until we kind of move to when we only have a sample variance. So let's say, I think here, I end up giving you, just to make this easy, I think I said the population variance is 1. So we could plug a 1 in there and we would know the standard deviation of our sample. So if I'm thinking about different values, right? How do I know, like if I see 4.5, how likely or unlikely was that? Or if I see 6.7, how likely or unlikely was that? 8.5, so on and so forth, right? Well, if I know that my sample means are normally distributed, and I see a value of 4.5, how could I determine how likely it was for me to see this value or anything further away if this was in fact the true mean? Well, if this is a normally distributed variable, I can turn it into a z-score. Could turn that value of 4.5 into a z-score. Look that z-score from the table, find the probability I saw something this far away from my assumed true mean or anything even further. So how would I do that? Oops. So how do I turn that 4.5 into the z-value? It's going to look exactly like what we were doing before. The only difference is now instead of using the true population mean, we use the assumed true population mean. Right? So if in fact this was the true population mean, 4.5 would be whatever the z-value is, that many standard deviations away from that assumed true mean. And if I was that many standard deviations away from that assumed true value, how likely or unlikely would that be? Well, I can look that up in the table. Right? Look up that z-value in the table, find that probability. So instead of calling it a z-value, because it's going to be a z-value we need for this hypothesis test, we start calling it a z-statistic. Now, the overarching term we'll use is a test statistic, right? But calling it a z-statistic kind of identifies it's coming from a standard normal distribution or the z-tables. So, in this case, we have what? Our value, the sample mean that we saw was 4.5. The assumed true mean was 7. I gave you the population variance of 1, sample size of 36. We could turn that value into a z-statistic. Right? So I think, I guess we hopefully know what these are. Well, I guess I skipped away from this example. So, but let's say I calculate that z-statistic, right? And I look it up and I find that this is like 0.032 or something, right? So what we'll call this value is our p-value, okay? So the p-value is essentially the probability that I saw a sample mean that was this many standard deviations away from the assumed true value or something even further away. Okay? So that p-value represents the probability of seeing this z statistic, which another way of saying that is the probability that I saw a value for the sample mean that was this many standard deviations away from the assumed true mean or something even further. So once we have that p-value, right, it's going to be a little, we're going to compare it to a threshold that we set, right? So maybe the probability is 0.032. So, well, should I reject the null? Well, there's only a 3.2% chance of me seeing this as the sample mean. If in fact what I assume to be true was true, then yeah, it seems like it's a pretty unlikely event. Right? Now, if this was as high as like 0.4, well, there's a 40% chance, right, that I see the sample mean I did if that wasn't that true. Well, it's pretty likely. I back out, I'm going to reject the null. Right? So basically, when we have really low p-values, we're probably going to reject the null. So it was very unlikely for us to see this sample mean if in fact 7 was the true population. It'd be more likely that I saw that sample mean. Sorry, if the probability starts to get really low, then what that's really saying is it's unlikely what I assume to be true was in fact true, and it's more likely that my sample means are actually going to be distributed around a true population mean that's much lower. Right? So, I drew one here where I'm thinking about kind of a p-value for a left tail test where I saw something that was below true mean. Right? So anytime I have kind of a less than sign in my alternative hypothesis or a left tail test, right? Less than sign in my alternative hypothesis, I'm going to be finding the p-value is the probability I saw that z statistic or anything below it. Now, for a right tail test, the two tail test is going to be a little bit different, right? So I've got kind of mathematically, I have it written out here. But honestly, I think that the easiest way to look at it is here, right? So let's think about for a left tail test, I'm looking for the area to the left of my z statistic. For a right tail test, it would just be the area to the right of my z statistic, right? Because there, for a right tail test, I'm only kind of concerned with sample mean values that would go against the null that are on the right side of the distribution. But for a two-tail test, I'm only going to see one of these z statistics, right? So let's instead, over here, let's assume we have the same setup. Oh, my null alternative hypothesis for a two-tail test. Okay. So I see that same sample mean of 4.5, and I know the probability of seeing something that far away from the assumed true mean or anything further was 0.032. But the problem is what I didn't add in to my, how I was kind of talking about the left tail test earlier, is it has to be, what's the probability, the interpretation of the p-value be, what's the probability I saw something this far away from the assumed true mean or even anything even further that goes against the null hypothesis. Well, in the left tail case, I know I was only kind of looking at, for less than case, I was only looking at that left tail. But I only see one sample mean. So if the probability I saw something this far away from the assumed true mean or anything further that went against the null was 0.032, it would have been equally as likely that I saw a sample mean what? So this is 2.5 away. So it would have been equally as likely I saw a sample mean 2.5 above that assumed true mean, or even further. But for a two-tailed test, these also go against the null. Right? So I'm only able to observe one sample mean, but I know for every single value here, it would have been equally as likely for me to see something that was that far away from the assumed true mean that went against the null on the other side of the distribution. So for a two-tailed test, I'll see that same z statistic, and I can find the area in that left tail, but I have to remember, oh yeah, but I could have just as easily or just as likely seen something from the other side of the distribution that would have went against the null. And so I'll take the area that I find and multiply it by 2, right? Or add it to itself, right? So that's where this was coming from. For a two-tailed test, I don't necessarily always see a, right? I could have seen 4.5, found this area and multiplied by 2. Or maybe I saw something above the mean. Maybe I saw 9.5, and then I have to know, okay, I'll take this area and then multiply that by 2. So I wouldn't get too lost in kind of the mathematical way we write this. I think it's a lot easier with the visual. For a left tail test, I'm looking for the area to the left of my Z statistic. Right tail test, look for the area to the right of my test statistic. For a two tail test, look for the area that's more, I always say more extreme than my Z statistic, because that means, you know, if it's a left tail test, or sorry, if I see a negative Z statistic, I'm looking in the left tail. If I see a positive Z statistic, I have to look for the area in the right tail. So just saying the area that's more extreme, I just, wherever your test statistic is, look for the area in that tail and then multiply it by 2. So once I have this p-value, what I'm then going to do to make my rejection decision, finally almost through all the steps, is if that p-value is less than this alpha threshold I set, I'm going to reject the null. Think about it this way. Let's say I set alpha to be 0.05. What I'm really saying is, if the sample mean that I saw has a probability of being seen, the probability of the sample mean that I saw is less than 0.05, if what I assume to be true was in fact true, then I'm okay rejecting the null. Because if the probability starts to fall below 0.05, it's probably the case that what I assume to be true isn't true. And that the true mean is probably somewhere over closer to where my sample mean that I saw was. Right? So I'll set this threshold for alpha and say, look, if the sample mean that I saw has a probability, the probability I saw that or anything further away from my assumption falls below 0.05, I'm okay rejecting the null. Now, it could be the case that this, in fact, ends up being the true population mean, and I just so happen to see a very unlikely sample, but I'm okay with that, right? Because if the probability starts to get too low, I'm okay if I made the mistake. It's more likely that what I assume to be true, in fact, wasn't true. So if I calculate this p-value and it ends up being less than alpha, then I'm going to reject the null. If it's not, we'll say we failed to reject. So kind of our steps: determine the null return hypothesis, specify what our threshold cutoff point is, and we'll talk a little bit more about that next class. Calculate our Z statistic, look it up in the table to find our p-value, and then compare the p-value to alpha to make our rejection decision. Yeah.
For the two-tailed test, are you going to take alpha over 2? Or
So we're still going to compare it to alpha, because what we've done is we've taken the area, we multiplied it by 2 so that we could compare it to alpha.
Okay.
If you didn't multiply it by 2, then you would compare it to alpha over 2. What kind of normal convention is, because we start to use this p-value for other things, the actual p-value is the area in that tail multiplied by 2 for a two-tailed test. Yep. All right. I think I kind of ran out of time here, but we'll kind of go back over, talk a little bit about type 1, type 2 errors. I'll work through some actual problems. So we're kind of setting us up to kind of do more hypothesis testing on Wednesday. And I might get the next Excel assignment up there. We'll have not talked about any of it yet, but it might just appear there tomorrow because as I'm going to kind of get it ready so that as we walk through things Wednesday and Friday, you can start to chip away at that a little bit. Okay. All right. We'll see you guys on Wednesday. Try to stay dry out there.